Hi everyone, and welcome back to episode 4 of Science at Home with me, Dr. Dan Nickström. So I hope you've enjoyed the last 3 episodes. We've looked at a different object or technology around the home and figured out the science behind it. So this week we thought we'd look at another technology that's in practically every home and every car too. It's about 100 years old, the technology behind it, but the science has remained the same for the whole time because it works so well. What we're talking about is the radio. Somewhere in a studio, just someone talking into a microphone, which we covered in an earlier video, and we're able to hear that through our radio, through the speaker, which we covered in another earlier video. But how is that signal able to travel the whole way across the country through the air without any wires to carry it? How it's carried is by a thing called radio waves, okay? But how do radio waves work? Well, radio waves are all around us. We can prove there's radio waves here by tuning in a station. If we hear the radio, there are radio waves. There's even radio waves in here, in Hans and Greta's house. Over here, up here too. Even out here, on the high seas. There's even radio waves in here. Okay, so there's radio waves everywhere. They're all around us. But if radio waves are all around us and we can't see them, but they're carrying sound to the whole country, well, why can't we hear them? What are they? Well, believe it or not, to really understand radio waves, we first need to understand light. What is light? I mean, what is it really? Light is a wave, a very particular kind of wave. But in order to understand light as a wave, we're first going to try and understand a different kind of wave, a wave we're more familiar with. We're probably mostly familiar with waves on the ocean. So I'm going to simulate waves on the ocean here, using a container filled with water and some sort of an object that I can apply a force with. I can apply a small force to make a small wave that travels across. I can apply a bigger force to make a big wave that travels across. I can apply that force slowly, once, again, or I could apply that force very frequently, 1, 2, 3, 4, 5, 6, like so, to make lots and lots of waves quickly, one after the other. It's hard to really understand it at this level. So imagine if you were in a little tiny boat floating on the surface of this water. It would be a lot easier to figure it out. Let's go down and have a look. So if Big Dan up there taps the surface of the water slowly, the waves won't come very often, okay? They only come occasionally. If he taps the surface faster, the waves are going to come more frequently, okay? In physics, we say waves can have a high frequency, coming very often, or a low frequency, only occasionally. If he taps the surface gently, the waves won't be very tall. They'll be very small waves. If he taps the surface more roughly, the waves will be a lot taller. Now the height of waves, we use a word called the amplitude. The amplitude means the height of a wave. You can have a large amplitude, a tall wave, or a small amplitude, a small wave. Remember those terms. We describe all waves using frequency, how often they come, and amplitude, how tall they are. Remember that. Okay, so now we understand frequency, amplitude, and wavelength of water waves. Those rules apply for all types of waves. There's waves around us everywhere. Sound is a type of wave. It's a pressure wave that passes through the air. We can't really see it because it moves so fast. We're going to show the amplitude, frequency, and wavelength of sound on our oscilloscope. We can see the wavelength, which is the distance between the peaks. We can see the amplitude, which is the height from top to bottom. And we can figure out the frequency by seeing how frequently the waves passed. So a low-pitched sound, is just low-frequency sound waves. Yes. And a high-pitched sound is just high-frequency sound waves. So our ears can perceive the difference in the frequency of sound. A quiet sound is just a sound wave with a low amplitude. A loud sound is just a sound wave with a high amplitude. Quiet, loud, low frequency, high frequency. Quiet, loud, low frequency, high frequency. Okay, but what's this got to do with light? Well, light is a wave as well. Light is an electromagnetic wave. Okay, so if our ears are able to perceive the difference in the frequency of different sound waves, well, our eyes are able to perceive the difference of the frequency of different light waves. So I'm now going to use my oscilloscope to represent the difference between light waves. If we imagine low frequency light waves, that represents red light. Okay, red light is low frequency light waves. And if we work all the way up through the spectrum, all the way up to blue, blue is high frequency light waves. And in between we have the whole spectrum of the rainbow. So our eyes just perceive the difference in frequencies as color. So if we think about red, orange, yellow, green, blue, indigo and violet, they're just different frequencies of electromagnetic waves. Okay, but what's all this got to do with radio waves? Well, you might know that there are certain sounds that we cannot hear. If they're too high frequency, maybe dogs can hear them, but we can't hear them. And if they're too low frequency, we can't hear them. Well, the same thing is true for light. There are colors outside of the spectrum that we can't see. Radio waves are just really low frequency light waves. Okay? Really low frequency light waves. And because they're such a low frequency, they can travel right through walls. Just like, you know, if there's music playing in the next door house or in a room beside you, you mainly hear the bass notes, which are the low frequency. Hear it? The bass notes, that low frequency comes through the wall. The high frequency doesn't. The same is true for light waves. Okay, so radio waves are just a kind of a low frequency invisible light. So that low frequency invisible light hits the antennae, and that invisible light, which is an electromagnetic wave, is able to send an electromagnetic signal down to the radio. And it's able to convert that electromagnetic signal into an electrical signal that goes to the speaker, and that causes it to vibrate and make the sound. So we might be wondering what all the different numbers and dials mean on our radio. Well, let's take a radio station like Midlands 103. The frequency for that is 103 FM. So the 103 refers to the actual frequency of the wave, and the FN means frequency modulated. Well, what does that mean? Frequency modulated means the coding that you send in the message to say how loud someone is talking or what note they're saying is in the frequency. So little small changes in frequency, just like this, little small changes in the frequency of that signal represent changes in the signal, and that's transferred through the speaker. So all of this explains how a radio actually works. So I hope you enjoyed that, and I hope you got some understanding from it. So you can understand that it's these strange particular type of light waves that we can't see that are passing through the air, and they're what's carrying all of that sound to us. Hope you enjoyed that, guys, and I'm already looking forward to seeing you on the next video when we look at something different.